Hello, I'm Sneha Samui, the first year graduate student from Department of Chemistry.
Hi there, I'm Kara Brown. I'm a junior undergraduate in the Department of Chemistry, and in this project, we'll be looking at the spectroscopic investigation of molecular structure as connected to the 1971 Nobel Prize in Chemistry. To outline a brief history of spectroscopy, early discoveries by German physicist Joseph von Fraunhofer showed that the spectra of the sun's electromagnetic radiation had many dark lines, indicating that light is missing at certain wavelengths because of absorption. These dark lines are often called Fraunhofer lines, and they're collectively referred to as absorption spectra. This is one of the earliest examples of that. Continuing on in the 19th century, Gustav Kirchhoff discovered that each element emits or absorbs light at characteristic wavelengths, effectively creating optical fingerprints. And this was an important basis for analytical spectroscopy. Numerous scientists in the 19th century studied the spectra of materials that were just heated in flames or placed in electric gas discharges. And these spectra, composed of numerous bright, discrete lines, are called bright line spectra. However, up until this point, no theory satisfactorily explained the origin of these spectra or the reason why different elements have different spectra. Continuing on, in the 20th century, many major developments were made because of physicists' ever increasing understanding of the measurement of spectra of the hydrogen atom. For example, work by Niels Bohr in 1913 presented the first theoretical model that gave rise to quantized energy levels that were also in quantitative agreement with measurements of the hydrogen spectrum. However, this theory failed when applied to the next atom, helium. In 1925, however, Heisenberg and Schrödinger put together the theory of quantum mechanics, which allowed for the explanation of discrete quantized spectra, which we now observe today. Broadly speaking, spectroscopy can be seen as the study of the absorption and emission of light and other radiation by matter, as related to the dependence of these processes on the wavelength of the radiation. Spectroscopic techniques have been applied in virtually all technical fields of science and technology, but one major application of spectroscopy that we will examine today is the structural investigation of atoms and molecules. Two major umbrella categories of spectroscopy include the collection of absorption and emission spectroscopy. Another important relation that we must look at in collaboration with spectroscopy is the photoelectric effect. So the energy E of a photon is related to its frequency, nu, by the relation E equals h nu, where h is Planck's constant. So if we look at the incoming wavelength and frequency of a ray of light, that can be related to the energy of the emitted photon.
So, in continuation with Kara, I want to first discuss why this 1971 Nobel Prize is focused on and what's the key scientific achievements with this Nobel Prize is. So, Dr. Gerhard Herzberg was awarded the 1971 Nobel Prize in Chemistry for his key contribution about determining the molecular structure as well as molecular geometry using different spectroscopic techniques. And he mainly emphasizes on the formation of free radical species because free radical species are very short-lived and reactive species, and it's very difficult to study or resolve them during any chemical processes. So in this work, he studied different spectroscopic technique as the fundamental tool to observe that how molecules are structured and how they behave during any chemical processes, and in terms of the molecular structure, bond formation, and as well as the chemical reactions. And next slide. Before going to the main topic, I want to give a brief introduction about this Nobel Prize winner. So Dr. Gerhard Herzberg is the German-Canadian physicist and physical chemist, and he won the 1971 Nobel Prize in Chemistry. The key contribution of his work for this Nobel Prize is, as I discussed earlier, that he used a different spectroscopic technique as the fundamental physical tool to study the molecular structure, chemical structure, as well as the molecular geometry of the molecule in terms of in terms of bond formation and different chemical behavior during any chemical process. So next, this study mainly, as we know that spectroscopy is the important physical tool to study the molecular behavior and molecular behavior during any chemical process, and as well as the molecular structure and everything, which includes mainly electron spectroscopy or EV spectroscopy. This spectroscopy helps us to understand the energy difference between any ground state molecule and corresponding to its excited state molecule. And the next one is vibrational or infrared spectroscopy. This spectroscopy helps us to know that what functional group present within the molecule, as well as the bond energy and bond length present between two atoms within a molecule. And the another and last one is the rotational spectroscopy, which help us to know the molecular symmetry, like which one is linear molecule, which one is symmetric top or asymmetric top molecule. Later, Kara will discuss in detail about those techniques. So in next, I want to discuss how high resolution optical spectroscopy Dr. Hertzberg used to study the radical species. So the basic principle of this spectroscopy is we saw that in the very left, this is the absorption, this is the electronic transition spectrum, we separated by a particular band space, and within each absorption, within each electronic spectrum, the vibrational transition spectrum are separated by a proper band gap. And if we observe each vibrational spectrum, then we will find that each rotational lines are spaced within it with a particular line gap. So this cannot be possible without any high resolution optical spectroscopy. That's why Dr. Gerhard Hertzberg used this high resolution optical spectroscopic technique to resolve each of the rotational lines as well as each of the vibrational band more precisely and accurately to obtain accurate molecular structure. So in next, the main instrumentation for involved in this high resolution optical spectroscopic technique is that diffracting grating. So when the incident light beam will come from the light source and fall on the slit, this slit will help to narrow the incident beam so that the background noise will decrease and the resolution of the output will be decreased. It would be increased. And that will fall on the mirror and reflect from them. There it will fall on the diffracting grating. This diffracting grating helps to disperse the incident beam into different wavelength of light. And then that will again reflected from another mirror and fall on the sample. And from the sample, the transmitted light will parallelly come from there and will focuses on the detector, and that will create the signal or spectrum, which would be more accurate and precise and easily resolvable. So in next, as we discussed earlier, that this Nobel Prize lecture is focuses on the study of formation of radical species and how they behave during any chemical processes. So that's why they use flash photolysis technique along with the high resolution optical spectroscopy to for the formation of radical species. Because flash photolysis technique is a very well-known technique to study the transient or very short-lived species and study their chemical behavior during any reaction. So here the flash photolysis technique consists of two components. One is palm pulse, which helps to form the radical or very short-lived species, and the probe pulse will record the absorption over the time. So the ultimate process will generate the formation and absorption decay of the very short-lived species over the real time. Now, in the next, how Hertzberg implement this technique to study the formation and the chemical behavior of the radical species is here the figure A is the normal radical species of the diazomethane molecule, and figure B represents the deuterated absorption spectrum of the diazonium molecule. So from when the hydrogen is isotopically labeled with deuterium molecule, we can observe that 1414.5 angstrom spectral line will shift from A to B. So this signifies that the radical species which formed during the reaction that comes from the CH2 radical, but not the NH2 radical. And in the next figure also, this is the spectral shift when each of the hydrogen molecule will be isotopically replaced by deuterium atom one by one. So in this case also we can see that each spectral line at 1414.5 angstrom will shift from CH2 to CHD to CD2. And that signify that when the deuterium molecule are placed symmetrically within the CH2 radical, that means the structure is symmetric, not asymmetric and anything. And also the spectral lines, the spectrum is very simple, not very complicated. That also signify that the molecule is linear but not symmetric top or asymmetric top type. So that is how Dr. Harshberg explained that how high resolution optical spectroscopy helps to resolve each spectral line properly to study the radical species and to study the radical species during the chemical behavior of radical species as well as the molecular structure of it more accurately and precisely. And then
Another technique that Gerhard Hertzberg used in his investigation of molecular species and structure is infrared or IR spectroscopy. And the key principle of IR spectroscopy is that oscillating molecular dipoles are able to interact with oscillating electric vectors of the electromagnetic radiation, leading to resonant absorption, relating to the relation H nu equals H omega. And this quantum energy of radiation, which is equal to the quantum energy of the oscillator, induces just the ground state to excited state energy change. Here on the right, we can observe the stretching and bending frequencies of the vibrations that are characterized in infrared spectroscopy. There are many different types of instruments used to observe IR spectroscopy. However, they all contain an infrared beam source, a sample that may be directly measured or held within a sample holder, and a beam detector. Recent developments in IR spectroscopy often look to the attenuated total reflectance, or ATR, measurement system in which the sample can be placed directly on top of a crystal with a high refractive index, and then the light source can be reflected directly off of the sample. So there's limited preparation needed for these samples. When we interpret IR spectra, we can see that the signals that are recorded by the beam detector are turned into IR spectra using the Fourier transformation. And IR is an absorption technique, but it's often plotted as transmittance for publication. Molecular vibrations have frequencies in the range of 10 to the 11th to 10 to the 13th hertz, which is on the order of 300 to about 3,000 wave numbers. And what we see in this chart on the left is that many functional groups found in organic molecules have characteristic frequencies at which they absorb, which lead to the interpretation of IR spectra. In Hertzberg's work, he used IR spectroscopy and other vibrational techniques to characterize the ground states of many of the reactive radical species that he was looking at. One example is the characterization of these C2H2 and HCN species, which in their excited states present a different geometry than in their ground states. They're linear in their ground states, but they show this bent geometry in their excited states, which he was able to characterize using IR. An additional application is the characterization of interstellar media, such as this sample from a comet, in which different functional groups can be characterized based on the absorption in this IR spectra. Another technique that was used in Hertzberg's work was electronic spectroscopy, specifically UV-vis spectroscopy. And the basic principle of UV-vis spectroscopy is that electrons can be excited into a higher energy state. And when we observe these excitations in the UV-vis region, that means that the valence shell molecular orbitals are involved in this transition. And the excitation region of these transitions can be determined by the energy separation of molecular orbitals in our molecules of interest and also the classic quantum mechanical selection rules. When we interpret the results of UV-vis spectra, some important values to look at are the lambda max values, which indicate the areas of max absorption of the species. Additionally, the relation Beer's law, which which relates absorbance to sample concentration, can be used to characterize the absorbance of these species. And similar to an optical spectroscopy, the UV instrument works by having an illuminating UV light source, such as from tungsten, deuterium, or light emitting diodes, which are separated using diffraction grating or a monochromator. In Hertzberg's work, he widely used electronic spectroscopy to look at the electronic structure and the transitions of reactive species, such as radicals and species with forbidden electronic transitions. An additional contribution that he made in the field of spectroscopy was the development of vacuum UV spectroscopy, which looks at wavelengths in the near UV region on the order of 10 to 200 nanometers, which allowed for the study of high energy electronic transitions. Overall, Hertzberg used a variety of spectroscopic techniques, such as optical, electronic, and vibrational spectroscopy, to do widespread characterization of reactive species, radical species, and chemical reactions.